afternoon. I think we'll make a start. Clearly I'm not Toyama-san. He's still at lunch, so I am going to look after this session for him. Up first we've got Mark, who's chatting to us about 2x enabling SDN, becoming a 2.6 exchange. So if you welcome Mark to the stage, thanks very much.
Bonjour. Hi, everyone. I'm going to talk about the experience we had at Toulouse. Toulouse is in France, and we put together during my thesis an architecture for the local internet exchange. Now I'm continuing that research in Tokyo University. I wanted to share with you here APRICOT, all things has been done and a different step, and mostly what we learned and the design is called Umbrella that we implemented at Toulouse Internet Exchange. Just want to go back quickly of what is Internet Exchange and where we were focusing in terms of design. Then an Internet Exchange is a network facility where more than 3 AS can peer together, and obviously it's localized mainly in big cities. The main benefits is lowering latency, reducing the transit cost, and improving the security. But what we have in the middle of it, in the center of the Internet Exchange, is switching fabric. It's a layer 2 switching fabric where the different operators with their routers can peer together and or peer with the root server and exchange their prefixes. But they use the facility of the switching fabric, metropolitan base usually, just middle of that. Then what we wanted to look into the approach with SDN is especially on the switching fabric. And the issue that we have today with the switching fabric, the very first one is the broadcast traffic. The broadcast traffic, I'm talking about the ARP broadcast traffic, and it needs to be handled very carefully because you need to get a lower level of ARP broadcast traffic, because all the CPU engaged in that domain have to check all the ARP requests because they need to know if they are for themselves. Then CPUs there have to handle different things, the BGP peering, different management and monitoring. And the CPU, if it has to check a big amount of broadcast traffic, it can spike or even get flapping condition on your BGP. You need to be protected. Solution exists, but that's just mitigation. I'm talking about rsponge, for example, with a script who reply to ARP or reply this not ARP requests who are not replied. But just keeping kind of low the level of traffic, because if you have a loop in your topology, you will create a broadcast storm. Then it will be replicating all the broadcasts. It will shut down your entire switching fabric, your entire Internet Exchange. Solution exists from long time, spanning tree and others, but they are not perfect. Then the undesired traffic is hard to keep out as well. When you have different type of router connected to the Internet Exchange, they will be configured mainly differently, a different version of code, and they may send traffic you don't want. CDP, LLDP, the discovery protocols, BPDU for the spanning trees and so on, that not allowed on the switching fabric. They need to be kept out. Then the filtering there is not very perfect in the way it's done by the vendors. Monitoring is also too limited, and I'm mentioning here SNMP, when you have only this, or too complex, because when you have a sampling monitoring like NetFlow, SFlow, IPFix, and others, then you need to get a collector, you need to get a database stored there in an archive, and you need to search inside of it what you want to, and you need to install different servers to maintain that service. For small and medium is make it a little bit complex. Then the design goal for, we wanted to get an operator-oriented OpenFlow XP fabric, not to put very hard and complex and fancy fix that we can have with SDN, but just focusing on what is necessary, just to fix the issue that we listed just before. Just a vision of, obviously, what is non-SDN configuration. Not SDN equipment and network today. They're all on closed SaaS and vertically integrated system and equipment. The application here that we have on the boxes just are the management, the routing part or switching part. They need to communicate with others on the distributed control plane. The operating system and the special packet for forwarding the packets to ASICs, they're also closed, and you cannot really access them. Analogy here is that obviously that type of equipment look like the same type of equipment that we have on the 70s, before the 80s, when we get the first PCs, with the open architecture of the microcomputer, who started with IBM on the beginning of the 80s. But when you buy such equipment, you buy a lot of different things. A lot of different things you don't need. A lot of functions and facilities that there exist there. And the only things you do here, you try to configure or deconfigure just for your need as an Internet exchange. And the Internet exchange is a simple, kind of simple layer 2 switching fabric. Then you don't need a lot of the different functions space for layer 3. Then there, you buy all those things and you just allow to manipulate the different state and the different configuration only, but you're not able to configure it. What come up with SDN, that's the decoupling of the control plane and the data plane. The fact to be able to do it is because they come up with OpenFlow. ASICS vendor and Broadcom first started to open the driver at the lower level to be able to manipulate the hardware table inside the ASICS. And from there you're able to add different rules or OpenFlow rules inside your ASICS itself. Then there you can have a centralized function and control plane. Then everything is seen from a centralized point. This centralized point gives all the information to be able to run the entire network. And the fact to see the network globally from a central point gives different facility was not possible with the distributed control plane that we had before. But one thing we really realized when we started to use and testing the OpenFlow switches, software or hardware OpenFlow switches, when you start, when you put your switch, the first thing it does is absolutely nothing. It just blink red. It may bring up the port if you had it to the bridge, but it does nothing. It just drops every packet. Then from there, we just wanted to add the very simple rules just to be able to fix the issue that I listed before. Then he starts and he boot there and he does just what we want, but not all the things that has been on the legacy type of switch, non-SDN switches. It's just focusing as we want for an oriented switching fabric, operator-oriented switching fabric. Then what we wanted, first of all, we wanted no more broadcast and a perfect edge filtering. No more broadcast. It means if you look what Internet Exchange is just, first of all, when you have a router of your member coming and to be connected here, you know the MAC address in advance because you have to register the MAC address. You know where you're going to plug that new router, and you know where it's localized. Then what does the broadcast for HARP is try to localize with the MAC address of the destination you want to reach on the IP level. And what we've done with OpenFlow here is just to unicast all the broadcasts and remove all the broadcasts away. Then we unicasted the destination and unique destination of the router concerned. And from there, there was no any more broadcast, no problem with the loop topology, closed loop topologies and situation like this. And he come up with also something with the pseudo wire concept that everything is isolated. The only traffic received by the members is the traffic at their destination and only what they need to receive. And they don't see other traffic at all. And we wanted something stable because if you look and you have a centralized control plane and you're running an Internet exchange at the size of the city, you have different POPs in different locations. If you have to get a new server for your controller in each POP, in any location, it doesn't make sense at the end. And then we wanted something who will be able to run for all the functions, for productions, without the controller, without the control plane itself. If you lose the connectivity, if there's a problem on a controller, on a centralized controller, you need to keep running. And it doesn't have to be all the POPs and all the localization running their own server. Then we wanted to be able to run as well on non-OpenFlow switches in the core, because that's where it's cost a lot, and the core switches could be recycled. We wanted to be able to use non-OpenFlow switches in place. What we've done for that is we use policy-based routing on layer 2, policy-based switching. We just have an access list MAC. We'll just check the very first byte of the destination MAC address and forward to the proper destination based on this information. This is one part of the design of Umbrella with the unicasting the broadcast. And the fine-grained monitoring with OpenFlow. When you have an OpenFlow rules, it come up automatically with a counter. Then with the rule we placed there, we wanted to get in details the full mesh view in a matrix that we can know in any destination to any members in any direction, just what traffic's been exchanged. And to have the lighter way, because all the counter are placed in a data plane, then most of the computing for the monitoring stay there. You just have to pull every 5 minutes just the counter, so it's very light. And you store that information in a very light database. Then most of the computing at the end is really done on the client, on the web browser, when they just access it just to graph on visualization. But it's very light type of monitoring and very fine-grained because we're able to see in any directions is that number of packets and amount of traffic exchanged. We get a link redundancy with group fast failover. Group fast failover is a function of OpenFlow, just checking the states of the POR and activating the backup in a bucket. And just based on the topology we use that function for link redundancy and failover. We evaluated the entire Umbrella architecture to see with the biggest internet exchange if they can obviously scale. It will be able to, with actual OpenFlow switches and their limited resources to be running with the Umbrella architecture. It does. And actually, if you look for 750 single MAC addresses or the more, 3 rules per member connected, Then you go a little bit to more than 2,000 rules. And the smallest OpenFlow switches today are running 1 gig. They support easily more than 5,000 or 10,000 of rules today. Then even the biggest internet exchange topology can be supported with the very smaller table size today. The bigger ones, we talk about millions of flow. Then there's a lot of space when you go for OpenFlow switches with millions of flow capacity. And everything's there oriented for operation and robustness is open for future application, and it's open for different application you want to develop for taking care of interconnections with MPLS and VLANs and different type of application taking care of the BGP and different side. Then now coming out of the experience, then the Toulouse Internet Exchange. Toulouse is in the southwest of France. Who doesn't know, is where Airbus plane are made. The A380, A320, all those planes are manufactured, and headquarters of Airbus is localized there. But it's not really in the center of France. It's most of the fibers are just coming from Bordeaux or Montpellier. There is only 2 feet, 2 directions, and the Toulouse Internet Exchange is a small one. Most of the fiber are all concentrated in Paris, or even Marseille with the sea fibers coming up, and Lyon, where the better connection spaces between Switzerland and Italy. But Toulouse gets small, and there was also something make easy to talk about that architecture and propose that to the Toulouse Internet Exchange. Then, because of the amount of traffic, and they were interesting about research and innovations, and get a different type of story. This Toulouse Internet Exchange was founded in 2006. It's member of Egress. Then we had 4 POPs around the city. With 10 active members and 300,000 IP prefixes, most of them because we do interconnect with France IX and Lionix, with Lionix giving us a view of their root server who increased the number of prefixes that we can see at the Toulouse Internet Exchange. Then the migration itself. And first of all, this is the topology that we had before. And as you can see, there's not redundant type of topology. They had the configuration for spanning tree, but they never really succeed to turn it on. Based on voluntary engineering, they tried to turn it on, but at the end it was working, and those guys were just running to the different POPs if something failed and replacing the equipment or things like this. But they were keeping stupidly the topology that way. And we come up with a choice that at that time, talking about 2.5 years ago, there is the approach of the white boxes, and the PK8 white box was one of the switches was supporting Open vSwitch. And Open vSwitch support multi-table with OpenFlow 1.3, and is running fully native because most of the switch to support OpenFlow those days are running on hybrid mode. They still run as a legacy on different port. You can configure which port you want to run on OpenFlow, but it's sharing resources. We wanted to get the full box and the full capacity of the hardware natively with only OpenFlow. And the switch itself was 48 1 gig port, and with a few 10 gig port in the back. And we come up with this topology, the 3 POPs, because the 4 POPs are 1 member only. Then 1 member only, then there was no other members who could be connected in the future. Then we decided to get that fiber back and remove one of the switches to reduce the complexity of the Internet Exchange. And you see here all the old and legacy switches has been used for the control channel. We maintain the old Cisco in place just to get open flow interconnections for the statistics and the control plane itself, and also to interconnect the France IX, because France IX maintain a different VLAN that we're sharing with Paris for members who need to be connected to France IX as well. We increased the capacity to 10 gigs links of the Internet Exchange. And we get a closed loop. We get full redundancy and capacity there. Then we had to develop the Toulouse 2.6 manager. Then now there's no anymore CLI, no anymore configuration of the switches itself. Everything is managed through a web interface where the member can add the new router and he configure automatically the different part of the Internet Exchange to the root server to the switching fabric itself. And it also gives statistics. Here we see a block diagram where the different information also graph and it is generating all the open flow rules and pushing that automatically. That the members managing directly their interconnections. They have access to their statistics. They can only see the traffic and not the traffic of others, could be competitors, and then they know the traffic they're changing with others. One thing we're about to add is then they can have about 10 open flow rules. They can use whatever they want, including only as a destination or source the MAC address. And in this case, they can monitor and they can go to the layer 4 for their own monitoring and statistics or troubleshooting. We do with the 2.6 manager generate the bird root server config as well. Then everything is fully automatic. And the full performance that we have, it just pays through OpenFlow. Then here's the link on GitHub of the 2.6 manager. We're about to include this in other OpenFlow controller based on Ryu. Then we're working on getting our umbrella approach inside Faucet. Faucet is OpenFlow controller operator-oriented with a larger community, and but you can have access to the even out to the 2.6 manager, and soon will be coming another version. Then what's next is actually more than a year after I've finished my research and design and even implementation and deployment there. Then all the members, and including the France IX, the larger Paris Internet Exchange, they funded a research project to continue that approach, and then it's still ongoing. It's a new PhD candidate in place, which is Rémi Lapérade, and it's also a part of the work done is part of the Endeavour project. The Endeavour project is a European Commission H2020 project, research within industry with DKIX and IBM Zurich, the research networking department in Zurich, with the Université Catholique de Louvain, the last CNRS where I've done my PhD, and the University of Cambridge. And Queen Mary is the coordinator and one of the main contributors of the Endeavour project. And there's lots of information there, larger approaches including security, DDoS, mitigations, and blackhauling, load balancing, all based on the SDN OpenFlow, and including also ISDX was one of the Princeton-based architecture. We're running on the layer 4 type of routing on the Internet Exchange. I invite you to go there. There's a lot of deliverable, a lot of reading, a lot of information, more videos, and so on. Then, thank you. If you have questions.
Hey, Mark. great presentation.
Thank you.
Donald from Google here. Can you tell me what was the most important benefit for members of the TOOS IX after you converted to SDN?
Robustness and easy management, very easy management, because the internet exchange is voluntary based. Then obviously it means that if any change, then we had to find someone who has to run in some place. When it was not critical, it may take some time. Then you see in the topology itself, and it was open, not really fixed, but it's running, but they wanted something who can run by itself. That's the case for 2 years, and with much more capacity than they were expecting. Just I'm talking about the monitoring, the easiness to adding or removing new members if needed, and also the side effect is just the fact of like being here, talking about it, and communication, because we're the first European open flow internet exchange, and interconnections, it's also social interconnections, is another part. Thank you.
Mircea, Cloudflare. I'd like to ask you, how many controllers do you have?
We have one controller, only one controller. In fact, the controller, we even kind of lost it because we had to change different fibers on the legacy network, on the fiber interconnecting the legacy Cisco switches. For 2 months, the controller was off the switching fabric, but we can run with only one. The only things we lost here is the statistics. But at one point, they're not very critical. Then we have only one controller.
You don't have any backup in case it goes down?
In this case, because of the design, we can have a backup, for sure, but it's not really necessary, because what we kept at the critical inside the data plane, we didn't want to separate all the functions, like ARP, because ARP is directly programmed inside the data plane with the critical part. When you look at the open flow architecture, all of them dealing with layer 2, they use proxy ARP in the controller. Then the proxy ARP need to be there all the time to reply to all the ARP requests. In the case of the umbrella approach, he stay inside the data plane. Then one single controller, even if you lose it for a time, that doesn't matter. It keeps running.
Yes, and did you make any benchmark test? How many requests, flow requests per second can you handle?
Well, if you look, we tested it a lot, and that's part of the different part of the evaluation we made on the switches. But the design we come up is very proactive only. Then if you look, even for the larger internet exchange, they do about 100 new change on the layer 2 switching fabric only. What I mean by change is just hard remove or change a MAC address of the router. They need to be connected to the switching fabric. 100 change per net exchange. That, well, even we did tested it, but it doesn't matter because it's very, very, very slow type of operation and flow additions.
One last detail. What controller do you use? Is something open?
Yes, it is. Yeah, you can check on GitHub. It's Ryu, it's NTT Python OpenFlow controller. Then we develop on top of it an application. We haven't used JSON and just using the API. And the 2.6 manager is developed in Django, and we just interact just with JSON. And we use the Ryu there as entry point for the API. And we could be even other controller in this case. What we really added to Ryu, just simple functions to be sure that when the controller come back up, it get exactly the state that it was expected before, and to maintain the states of the switching OpenFlow tables. Yeah.
Thank you.
Thank you. Any other question? Thank you very much. Yeah. One question.
Hi, Mark. Hi, Eric from ARM6. So just a question, because I'm not really familiar with OpenFlow. How do you add a new links of a member in? Would that be that you're gonna have to create like a one-to-n flow for that new member. Am I correct?
When we add a new member to the switching fabric, how we do it, you mean? Or?
Yes, that's correct. Because basically, from what I understand, there is no mark learning.
Yeah, it's no mark learning, because when the new member come up, he has to go to the form, then you have to fill. Like in AM6, you have on the portal, the very first portal, you just add which highest number you have, and even the MAC address, which speed port you're going to connect. And from there, you check on your back office on AM6. Then we do the same here. We just select which port and physically will be connected. Then we know the MAC address. Using that MAC address, we generate the open flow rules automatically, and is there pushed to the switching fabric. But obviously, the member have to physically connect his port to the open flow switches at the edge.
Okay. And when that MAC address changes, then that would mean you need to update your flow entry all over again.
Yeah, if the MAC address change, we need to be informed before. He has to go to the form again. He change it, and then in this case, he have to apply. It's a period of time. Then we had the two ones. Then he can easily have the two MAC addresses, but he has to be only one at the end. Then it's a small procedure for applying the change. Yeah.
Yeah, but I think it will be much easier, right? Because you're in control of the controller. You can just really set it on all the equipment. Right, that's clear enough for me. Thanks.
Thank you. Thank you. Bye-bye.
Thanks very much. Next up, we've got Tom from Fastly. Tom's going to chat to us about minimal viable FIB. So please welcome Tom.
While Tom is getting on stage, I haven't received any more peering personals yet, so if anybody wants to send me a peering personal, either email me or come over to my table with a USB stick. Thank you.
Hi everyone, my name is Tom Daly, I'm with Fastly. For those of you that don't know, Fastly is a content delivery network spread across 35 POPs around the world. We have about 10 terabits of edge, 200 peers, and we're present at about 37 different IXPs right now. We're a little bit different than most CDNs from a technical architecture standpoint in that we have some very distinct design constraints that we use as core tenets to our architecture. And so at Fastly, we have no big box routers whatsoever. We also do not have any load balancers. Now, what we do have is Linux, top of rack switches, and a bunch of BGP tricks. And what this talk is going to be about is some of those tricks that we play in order to make the CDN work, and how we derive what we call a minimum viable FIB for the purpose of peering. So let me take you through how traffic egresses from one of our cache servers at Fastly. We have very, very dumb switches in a top-of-rack edge router function. On the inbound side, the switch acts as a stateless ECMP-based load balancer. And we've written a bunch of software that runs locally on the switch in Linux in order to maintain consistent ECMP hashes and to perform health checks against our cache servers. Now, that's basically a layer 3 relationship on the inbound side. But on outbound, as we're talking to transit providers, bilateral or multilateral peering fabrics, we certainly do not have the FIB scale on these boxes in order to use them like a traditional router. And so for transit providers, we came up with a unique trick to allow cache servers to directly access the L2 egress next hop for each and every transit provider. So we also wrote some software that manages those egress MAC addresses on each of our cache servers. Now, finally, we need a way to move the routing information around. So what we do is we run Bird, the BGP routing daemon, in userland on the Linux-based switch. eBGP sessions from peers, transit providers, are terminated on that instance of Bird locally. And then we reflect a table down via iBGP to each cache server. And finally, just in case everything goes completely wrong, we have multiple default routes out to transit providers from that switch in case everything should break. But we want to do better than breaking. So here's a graphical representation of what inbound looks like. Traffic comes in from the internet, from one of our peers or transit providers, hits the FIB on the switch, and then is ECMP sprayed to a cache server in blue on the right. Again, this is layer 3. On the outbound side, it's a layer 2 lookup. So packets are directly egressed from the cache server to a transit provider, simply using the layer 2 forwarding complex on the switch. There's no layer 3 operations happening here. And it's really important for the rest of this talk that you think of this constraint as being L2 egress. So we are at many IXPs, as I mentioned earlier, and I've excerpted a couple rules from the LONAP technical manual that create some of the constraints that we have when we want to show up at an IXP. So first, members must only respond to ARP requests for MAC addresses for which they've been assigned. So that means one MAC address. And you must only present one MAC address at the IXP. And finally, you have to make sure that anything you're doing at that IXP as an attached member is not detrimental to other members on that IXP. And so you can imagine attaching to an IXP, the purple box, in a full layer 2 mode is going to be a big problem. You're going to leak a bunch of different MAC addresses from your cache servers to the IXP. That'll trigger port security. You will potentially leak broadcast traffic to the IXP, and that could potentially leak some sort of internal broadcast traffic that your network might have that might be sensitive. So you certainly don't want that to happen. So how do we get to an IXP? Now, one of the things we can simply do is turn that switch into a layer 3 router on the outbound side, just for attaching to the IXP. But again, we still have the FIB scale problem. So here's 2 popular peering exchanges. One is Equinix Singapore. The other is AMSIX in Amsterdam. And you can see from the MLPE route servers in Singapore, we're seeing about 60,000 prefixes coming in. And in Amsterdam, as you would expect many more, about 239,000, 240,000 prefixes coming in from the MLPE route servers. And so if you try to import that into your FIB, you get a really unique error message. And it looks something like, routing hardware resource full, hardware resources are insufficient to program all routes. And when you do that, if you let that happen, there is a good chance that your switch turns into a partial black hole. And that's certainly not good for our customers, so we don't want that to happen. So we have layer 2 attachment as a problem, we have route servers as a problem, and we have the FIB limits ultimately as the problem in these switches. And so this table summarizes a lot of the FIB limits that we run into with the different switch models that we have deployed in production. So we have FM6000, we have single chip Trident 2, we have multi-chip Trident 2, we have Arads, we have Tomahawks, and we have Jerichos. We have a big mixed mass of switches in our network, just as we've followed different generations of silicon. And you can see that the IPv4 FIB is somewhere less than about 100,000 routes on these boxes, except for the Jericho. And we just have Jericho coming into our lab, so I'll make a couple remarks on Jericho at the end. But certainly not going to fit something like Equinix Singapore into the Trident box unless you're using LPM mode. Certainly not going to fit into the ARID box, and you're not going to fit something like AMSIX into an ARID box where you're looking for a 100 gig interface. So it's quite a problem. So just to review, we have problems at IXs. We can't L2 egress to them because we have multiple source MACs. We can't spoof the switch's source MAC itself as packets run through because the switch certainly doesn't want to see its own MAC address learned from another device on the network. We could potentially leak ARP, broadcast, or multicast, and it's really, really bad exchange hygiene. I'm sure there's a number of exchange operators in the room who would not like it if anybody did that to their exchange. And on the L3 egress side, as I said, the FIB is just too small. We have problems with route servers. And we also have peers with lots of prefixes, bilateral peers with lots of prefixes. And so when we did this, we also knew that our solution needed to support v4 and v6. So we came up with this concept called the minimum viable FIB. And we said, look, at a multilateral peering exchange, given the fact that we're a CDN, and we have 35 POPs around the world, not all prefixes are necessarily valuable across the entire geographic footprint, because a CDN node at Fastly is meant to serve a particular portion of the world. So you don't actually need to carry traffic across a backbone. So what we said is, let's manage the FIB size as related to the value of those prefixes. And so the value is defined as high-value ASNs and prefixes that are local to the POP. They're geographically scoped to the point of interconnect. And then they're valued through traffic utilization, and they're valued through the performance that they give to our network. And all of this, I want to emphasize, is always backed up by transit default routes. So if something goes drastically wrong with this system, you're just going to be heading out on transit. And that's fine. We're okay with that. So we have a tool at Fastly that I want to tell you about, and it's called BigPeer. So BigPeer, it's built on Bigtable from Google. It's our internal peering database. Now, that helps us get a sense of what our peering world looks like. It lets us preference bilateral peers over MLPE routes, over transit. It contains a bunch of information from S-flow exports from our switches. That gives us traffic volume. It pulls in IRR data using BGP Q3 as a tool set. And that allows us to watch for max prefix and prefix origin violations from our peers. And then finally, we also run a BGP route collector. So that way we can collect routes and have a feedback loop to dampen churn in route selection for this tool should we need to. So how does BigPeer work? Well, what BigPeer does is it creates a complex prefix list for us. So on the left you have the first few lines of output from BigPeer running against the Singapore Equinix exchange, and on the right you have the first few lines of output from the MZIX exchange. And you can see you have different prefixes that have made its way through the permit filter for those respective exchanges. And this kind of points to the geographic distribution of these prefixes being useful to us. We're generally not going to serve traffic for Amsterdam out of Singapore, and we're not going to serve traffic for Singapore out of Amsterdam. That's not the business we're in. So BigPeer gives us a list of top talkers, which we can then filter against the exchange's import session. So now you get a switch FIB state that is far more compact. On the left in Singapore, we happen to be using some FM6000 based switches. You can see that we program about 26,000 routes into the FIB. The exchange had about 60,000 routes on it. The hardware was capable of 70,000 routes. We said, look, we still want more headroom. We need to IPv6 in here as well someday. So let's just program about 25,000 routes. Now over on the right in Amsterdam, where we had about 240,000 routes from the MLPE route server, you can see we're programming about 22,600 routes as having great value to us in Amsterdam. Anything else will just go out over transit. So now we have plenty of FIB headroom sitting inside these switches. So you can see that in a place like Singapore, this is a parset between target ASNs and peers that we're using to egress traffic. We get about 70% of that POP's traffic delivered over peering using 25% of the MLPE routes that were available to us. Didn't need a big box router for this, just needed a little bit of software. And if you saw this talk back at Global Peering Forum last year, we were just getting started with this. And we had successfully, offloaded traffic or offloaded prefixes using this tool. But there was another variant that came from this work, and we call it /peer. So /peer now manages P&I bandwidth constraints. So if we have, say, a 10 gig link to a peer, and there is more than 10 gigabits per second of egress traffic to go through that link, we can fire up /peer. And what /peer will do, similar to selecting routes from the MLPE, it will go back to our S-flow collector, and it will say, hey, I'm looking to fill 9 gigs of traffic at peak onto this link. What prefixes should I include to fill this link up with 9 gigs of traffic? And so it's this software process that sits there and essentially plays Tetris with our flow data to fill up the link to about 90%. It generates a set of prefix filters against the peer's BLP session, and we no longer have congestion on PNIs. So there's a bunch of future considerations and a couple questions I've received in the past about this software set is, look, this software is going to be irrelevant to you as soon as some of the next generation routing kit hits the market. Earlier you saw my summary of the Jericho-based switches, which are now running 1 million routes in the FIB. So did we do this work in vain? And we don't think we did. Because number one, we have an existing install base. We can't go forklift upgrade the network overnight. We have a capital plan we have to stick to. But we want to start doing things like introducing BGP add path for fast routing reconvergence and multipath through peering exchanges. And that's only going to cause more prefixes to need to get injected into the FIB. We want to have plenty of room for IPv4 and IPv6 growth. And /peer, as I just told you, puts us in a place where we can keep PNIs running warm, but not absolutely hot and falling over. So that is a big peer and /peer at Fastly. It allows us to optimize the way we use FIBs in top-of-rack switches. And if you have any questions, I'm happy to answer them. Hi, Will.
Hi, it's Will Hargrave from Lonap. Question unrelated to perhaps to IXPs directly. You obviously take this data and you may have a situation where you have a BGP session with someone, you're accepting a bunch of routes from them, and they may be debugging it on their side and like, what the hell, I'm sending them this route, but you're not sending me any traffic via it. Do you expose your decision-making process to peers to help with that process, or?
We have not done that yet. And so I can understand that being problematic for a peer. We are looking at implementing a global looking glass, not only for our customers, but for our peers, so that way you can come in and look at the table from our side.
Great, thanks.
Hello.
Hi.
Hi, Kaver Einfer, RIPE NCC. I saw you said you're also processing IRR data, which is very nice to do in that level. Have you considered RPKI, or have you done anything? I know there is a lot of overhead to process that data, but many think that would be the future. So,
we have not yet considered RPKI.
Mm-hmm. Okay. And for the looking glass, for you and anyone else in the room, if you know, RIPE NCC runs RIS, Routing Information System. And we are actually developing a new type of looking glass, BGP looking glass, on top of RIS. And if you're interested, we can talk about that, and we can also implement that to put it in your own network as well.
Why don't we have a chat about that offline?
Sure.
Thank you. Thank you.
Thanks, Tom. Raf, do we have any peering personals?
We have one.
We have one. That lucky person gets half an hour.
Yeah. That's right. Yeah, can you just scroll to the section 2? Yeah, we've done that. Yep. Twitch. You have half an hour. You can tell some jokes. If anyone else without the slide want to come up and introduce their network, please feel free to come up. Even without a slide. We've got for half an hour. I mean, we can start doing karaoke.
Don't make me sing here, okay?
Gangnam Style.
Hello, my name is Brian Kim. I'm in charge with the Asia Pac ceremony-free interconnection here. You can just call me peering guy here. So Twitch, our AS number 46489. Our traffic profile is mostly content live streaming services. Our total traffic volume is over 1 Tbps plus. And our peering policy is selective, meaning then we love eyeball networks to be peered. Okay, for the private peering spots, In Asia Pac, will be Hong Kong, Seoul, Tokyo, Singapore, and Sydney. For public peering spot in Asia Pac will be IXNSW, Equinix Hong Kong, Equinix Singapore, Equinix Tokyo, Hong Kong IX, Kings, JPNet, BBIX, Mega IX all over the Asia Pac. And you can find us at the peering DB entry at as46489.peeringdb.com. And you can just send us an email to thepeering@twitch.tv. Thank you.
Up next is Seishi from Google. He hasn't prepared a slide yet that made it to the system, but you can probably Google.
Okay, so I apparently sent the slides in too late, but my name is Seiichi. I'm with Google. You may have seen me before at my previous companies, but I take care of the APAC pairing these days. So our ACE number is 15169. Pairing DB records are there. If you want to meet up with us this week, we're around in the meeting rooms in level 2, or just find me out in the hallways. And since it's not there, my name is Seiichi again, and would really love to talk with you guys. Thanks.
Slides will be available online afterwards if you can't remember that. Last chance for anyone else who wants to jump up and do a quick improv personal. Nope. Okay. Well, I think we might break early for afternoon tea break. It's been served out there already, I think, so we can be back in here at, what was the next session? 4:30. 4 o'clock. Thanks, guys.